Do you know the difference between LRFD and ASD? What does LRFD stand for? What does ASD stand for? How are they alike and how are they different? And most importantly, how are these design standards applied to design our structures? In this video, we're going to talk about some good concepts that are often tested on the Civil FE exam. We're going to break down LRFD. We're going to break down ASD. So your challenge is to take your own notes, summarize what we're talking about into your own notes, into your own words, and you can always share your notes with me in the comments below. Let's start with LRFD. LRFD, the load and resistance factor design. Load resistance factor design. We consider both the load and the resistance, which refers to the material resistance as we'll define here. So load and resistance factor design, LRFD, is a structural design method that ensures safety by applying factors to both the loads acting on the structure and material resistance. So we consider the loads, we apply a factor to that, we'll see that below, and we also look at the material resistance and apply a factor to that. Both the load and resistance is the material resistance. So it is a reliability-based design approach that incorporates uncertainty in the loads. These are the service loads. These are the real loads. When we say loads, it's the service loads. So we're going to account for that uncertainty of these loads. And also the material properties, both the loads and the material properties, which relates to the material resistance. So it's going to optimize the use of the materials while maintaining a consistent level of safety. So here's a graph that we'll see both for the LRFD and ASD. So in this case, there's special terms that are often confusing for a lot of students, even for me. The nominal moment, the design moment capacity, design flexural strength. You know, there's a lot of these terms. As we continue to practice in the course, we'll see how we apply those and what those exactly mean. But here we're going to stick to the basics. We're going to go with the moment. Keep in mind, it could be the shear here that we're talking about. Let's say Vn for shear. This is the design shear strength, the design shear capacity. That means the same thing. We have the moment, M for moment, the design moment capacity, the design moment strength, the design moment. So here, N stands for nominal. Keep in mind, nominal is like theoretical, perfect, ideal. The equations are derived under ideal lab conditions, theoretical, nominal. Then we can also have the Pn. So Pn is going to be the one with the P is for the compression. We see that in steel design and also concrete design. So that's going to be the design compressive strength, design compressive capacity. And all of these, keep in mind, are nominal. So what this graph is showing here is we start with Mn. That's going to be the ultimate strength. So it goes on the stress versus strain diagram. We go to the very top at the ultimate. So we can get that. We can get that as a theoretical value. That's the ultimate strength of the material, theoretical, nominal. Now, in this case, we're using an example of Mn for the moment strength, the flexural strength. It can be Vn or Pn. In this case, we're using Mn. So what we will do then is get the LRFD capacity, the one we're focused on here, in the green. And notice what happens is we reduce this. We want to be more conservative. We want to be more on the safe side. We reduce the strength. We're like, yes, the theoretical strength is this, the nominal strength of the member, but that is theoretical. That's nominal. I'm going to reduce it to be more on the safe side. So we're going to lower its strength, give it less strength by applying the phi factor. We call that a resistance factor. It's not a safety factor, it's a resistance factor. And this gives us the design strength of the material, of that W shape, of that concrete beam, the design flexural strength, the design moment strength. This right here is LRFD. Notice now something important. The yield point is somewhere here. LRFD doesn't have to be in this elastic region below the yield point. It can be a little above it. It can be at the yield point. It does not have to be in the elastic region. In this case, where when we look at the ASD capacity, this is the ASD design strength of the member, we account for this. This is called our omega. This is like a factor of safety factor. So we take the starting nominal strength, we calculate that using theoretical equations that are derived for us, and then we reduce the strength and get the ASD capacity. But now notice the yield strength is here. We're in the elastic region for ASD. So ASD is always going to be below that yield point in the elastic region. It assumes elastic behavior. That's the big difference here when we look at these. So this is for LRFD, this is for ASD. This is good to visualize, and we'll see that under the ASD section. So now focusing on LRFD, we're looking at LRFD. Let's say, for example, just to give you a very simple example, let's say we have a beam and we take our beam here and we're going to be like, okay, for this beam, something simple like this, let's say it sits somewhere on two ends. And I'm going to be like, okay, for this beam, I know that I want it to be designed to hold 100 pounds. But what I'm going to do here using LRFD, I'm using LRFD design method, is add a factor of safety to the load. So what I'm going to do is overestimate the load. What LRFD does is look at the load and overestimate it. So we're going to give it more load when we're actually designing this. So we overestimate the load to be more on the safe side, and we apply that by a factor. That's the load combination factors that we see in the FE handbook. So I'm going to apply a factor of 1.6. So to this load, I apply a factor of 1.6. So now the real load that I'm going to overestimate is 160. So here the load that I have is actually going to be that 1.6 times that 100 pounds, and it becomes that load of 160 pounds. So this is the load that's applied. I overestimate it using LRFD. Now at the same time, for LRFD, the material strength, let's say it's 200 pounds. So this material could be, let's say, steel, concrete, it could be wood. So the typical ones in our case for the FE, steel and concrete using LRFD. So we know, let's say the material strength of this will be 200 pounds. What I'm going to do then is be, again, more conservative and reduce its strength. Give it less strength when I'm designing. So it's 200 pounds, the strength, but then I'm going to apply a strength reduction factor of 0.9. That's actually the phi value. So we're going to account for that and reduce its strength, reduce the strength of that material. So then the real strength is the phi here, that 0.9 times the 200, and it gives me 180. So the strength here is going to be the 180 pounds. Now that is that. So we have this crucial number, 180. We have this crucial number. We overestimated the load of 160. Then with that, since the 180 pounds, no, this is the reduced strength, is greater than the 160. This is the applied load that we overestimated. We know the beam is considered safe. This 180 is bigger than the 160. In this case, this satisfies our design requirement, and we would say this beam is safe. If it was the opposite, let's say this was 200 and this stayed at 180, that would not be safe. The load here that we overestimated would be bigger than the strength, the reduced strength of the material, and that would not be safe. In that case, we would have to select a different W section, a different material, make some adjustments, or look at the loads more closely, get a better approximation to ensure that the strength of the material is always bigger than the applied load. This is really LRFD. That's what it's doing. So now, looking at practical equations that we see in the handbook, LRFD applies load factors to various loads to account for their variability. Typical load combinations are shown. So find this with me in your PDF in the handbook. Loads per ASCE 716. These are nominal loads. These are theoretical loads, the real world loads. And we have LRFD, ASD, D is dead load, E earthquake, L is live loads for the floor, LR is live loads for the roof, R is rain load, S snow load, W is wind load. Now looking at LRFD load combinations, we can say if we compare all of these, we choose the largest. If we compare these two, we choose the larger of these two. Now, the big ones are this. Typically, we deal with this one. We use this so often, 1.2 dead times 1.6 live. No, these load combinations are used to overestimate the load. The D here is the nominal load. These are the real service loads. We call this real life service loads. We're going to overestimate them to be on the safe side, account for their probability of occurring. And notice we attach a bigger value here, a bigger factor for the 1.6 L for the live load, because that live load is more unpredictable when compared to the dead load, which is just permanent. Dead load, let's say the self-weight of a beam, the self-weight of the members that we have, those are more predictable, right? But the live load, it has more unpredictability, so we attach a bigger factor to that. So we're increasing the load in all LRFD using these load combination factors. Now let's look at the typical steps for the LRFD design process. So this is the process when we analyze problems or do those design calculations. So this is important to know these systematic steps that we will apply. Number one, identify the loads and calculate the ultimate strength. So we want to identify the loads, the dead load. Dead load is like the self-weight of the members, self-weight of the columns, the beams. We can estimate that easily. We have the volume of the member, we have the unit weight of it, concrete, steel. We can get that load acting down due to gravity. We call that a dead load. Dead loads are always permanent loads. We have the live load. These are non-permanent. It could be, let's say, couches, chairs, people moving. So these are non-permanent. And it all depends on the occupancy. Let's say it's an office space or it could be a manufacturing building that will have different live loads. And we must estimate that good as well. And it depends on the standards we're using, the steel standards, the ASC standards, and so on. Wind loads important, and if we have lots of strong wind, let's say in Oklahoma, here we have a lot of strong winds, depending on the location. So we want to consider that depending on the location. Snow loads as well, similar. If we have a lot of snow, we must consider that. And also earthquake loads, let's say, for example, earthquake regions like California. So now, for example, what we will do is, for this one, is look at the MU. MU stands for the ultimate moment. This is the ultimate bending strength, ultimate moment. M always stands for moment, ultimate flexural capacity, ultimate flexural strength, and so on. We use different terms. It's confusing, but it all means the same thing. So the MU can be estimated. The ultimate strength requires strength factor moment. This represents the worst case loading scenario on the structure. Now, I want you to keep in mind, in this case, again, we're looking at the moment. Just as an example, this can be done for the shear, the ultimate shear, and also the ultimate compression. So we can look at the shear strength here and the compression if we're analyzing for compression. Here we're looking at bending. So what we will look at, typically we deal with this, is a simply supported beam. So we have a pin roller and we have a dead load and a live load. These are both distributed loads. What I'm going to do first is determine the factored distributed load. This is the ultimate distributed load using the load combination factors for the dead and the live. So that's all we have in this simple example. We have a live load, we have a dead load for this simple case. So that's the one that would control. We'll see through examples that we often see which one governs if we have more of these. For this example, we have two basic ones. So we get that ultimate distributed load, and here for D and L, this is the distributed dead load, which is this one, and this here is the distributed live load. They're both distributed loads, so I'm just going to substitute that in there and then calculate the ultimate distributed load. So here we're overestimating the load still, but it's distributed loads. That's fine. We're overestimating them using these load combinations, LRFD load combinations. Then what I can do is, with this calculated, I accounted for the load combinations. That's done with. I can then get the ultimate moment. This ultimate moment is actually in the FE handbook, right? We see that. If you're sticking with me, if you're in the course, we saw that in Mechanics and Materials, right? We use that at the end of Mechanics and Materials tables in the PDF, in the handbook. We can easily calculate that. It's just the maximum moment. So here what we have to make sure is put that in there. L is the length squared divided by 8. And we get here now, looking at the moment, the ultimate strength. So this is the ultimate strength that we just calculated. This represents the worst case strength loading scenario on the structure. That's step one. Get the ultimate strength and consider the load combinations always. Then step two is calculate the nominal strength. Nominal strength. Determine the theoretical capacity, theoretical strength of the structure based on the material properties. I want you to know, nominal is a common term used in engineering, so this refers to the ideal theoretical or standard value of a property or dimension. In our case, the property is the strength. So it does not account for real-world variations, tolerances, or safety factors. We're not accounting for that yet. Nominal values are typically derived from design calculations based on material properties and geometric characteristics under perfect conditions. Nominal. That's what that means, a common term often used in engineering. So this is the nominal capacity. So here are some examples. We see also equations under concrete design that we talked about before. We know we can calculate that using equations that are provided to us. So let's say for bending, again, we do the same for shear or for compression. For shear, it would be Vn. For compression, it would be Pn. We can do that the same. In this case, we can look at bending, and this here is for steel design. Concrete has its own nominal design strength, flexural strength, moment strength equation that we apply in examples. So this one is going to be if the plastic capacity controls. This is in the handbook. And this one, we compared the lateral torsional buckling capacity, which is going to be this one, to the plastic capacity, which is this. And the one that comes first, or the smallest ones, controls in that case. So this here is the plastic MP, which would be Mn, really, the nominal. And then we compare that capacity to this capacity, this number, and the smaller one would control, and that would give us that nominal moment capacity. So it's all nominal per equations, derived theoretical equations, or equations based on standards or empirical equations that are already given to us. These are the nominal and stands for nominal. So that is the estimate we need to make. Then we go to step 3. Apply the resistance factors. So LRFD, did we already consider the load part of LRFD? We did, right? In this, load combinations. So we considered we overestimated that distributed load. Good. So we're being on the safe side there. So now we apply again another resistance factor. So resistance factor, reduce, always, keyword, reduce the nominal strength using phi. The phi is always a resistance factor to account for uncertainties. So we're accounting for uncertainties, we're considering probability, and we're going to apply that phi factor by reducing that nominal strength. So here, if we calculate a nominal strength, we're like, okay, that's nominal, that's perfect conditions. I want to reduce it more. I want to be more on the safe side. So I'm going to apply resistance factors. So typical ones for steel design. Concrete design has its own. We know it's in the handbook. We apply equations. Keep in mind, we can use this for concrete as well. Concrete only uses LRFD, so we must know that too. So for steel design, just as example for bending, B stands for bending. We use 0.9 for shear in the handbook. B stands for shear here is 1, and for compression, C stands for compression. We use 0.9 for steel design per FE handbook. So that is going to be applying the resistance factor, and this would give us our phi Mn. So we take our phi times Mn and we multiply it by Mn to get the design. This would be the design strength of the member. Design strength, in this case, it's actually a moment strength. In this example, keep in mind, it can be shear, it can be compression as well. Bending, moment, flexure is what we're looking at when we apply the resistance factor, giving us again phi Mn for LRFD. Now, that was step 3. Step 4 is going to be check the design requirement. This is important. Design condition must be satisfied here. It's always this. Always. Write this down in your equation sheet. Ensure the structural element is adequate. So we want the design strength that we did reduce with the resistance factor. This here is the design strength, or we can call that design capacity, to be bigger, definitely bigger than the ultimate strength. This is the ultimate factor strength, ultimate strength of the material, ultimate strength. And if that's true, if this is satisfied, if it's bigger, we know we are okay. It's an adequate design. So here, if the design strength Pmn is greater than or equal to the required strength mu, the design is safe. Otherwise, if it wasn't, let's say mu here was bigger than Vmn, we know we need to make adjustments to the section or material if needed. So we may need to select a different section if that's not satisfied. Look at our tables, let's say W shapes, and select the section that makes this true. This must always be satisfied, and it must always be satisfied for shear as well. Here, the shear would be this, and it must be satisfied for compression as well in that case. So that is LRFD. Now ASD. It's really the same process in terms of the design steps, so we'll go through those fast. ASD is called Allowable Stress Design. Know what that means? Allowable Stress Design. So Allowable Stress Design is a structural design methodology that ensures safety by applying factors to the material strength. So we're looking at the material strength only for ASD. Keep that in mind. LRFD is different. So it's always the material strength that we look at, allowing the structure to handle the service loads without exceeding allowable stress limits. So it is a traditional design approach. So this is an older, more traditional approach that incorporates a single factor of safety. We call this R omega, applied to the material, ensuring a consistent and conservative level of safety. So this one here, ASD, is more traditional, and it will be more conservative because we're going to be in the elastic region for this, but it is not used for concrete design because we know concrete does not always behave elastically. In that case, LRFD is applied for concrete design, but for steel design, we can use LRFD. That's more commonly used nowadays. ASD is old school, it's traditional, it's more conservative, but it doesn't account for probability, reliability, and so on. So that might actually overestimate things, and that would cost more in terms of designing the building. So this is the traditional one. Now going back to this, Mn, we start with this, looking at the moment. What is this called? The design nominal moment, design moment capacity. So we start with that, we calculate that. That's theoretical using equations. Then this here is for LRFD. Let's focus on the ASD one, which is the one in red here. Notice again, it's below the yield point. We're within the elastic region, below the yield point when we calculate the design capacity, the design flexural strength, or the design moment strength. Here, this is per ASD. And note, look at this. We always divide by that omega. This right here is like a factor of safety. It is a factor of safety for the ASD. This one is for LRFD. The resistance factor is phi. Now, for example, here is another example. It's the same beam. So let's say we have our beam, and we know under normal conditions, this beam is designed to hold that 100 pounds. So we want to apply a factor of safety of 1.67 to the material strength. So this means the structure should have an ultimate strength of 167 pounds when we apply the factor of safety. So the material strength is going to be 250 pounds. The allowable strength is calculated as follows. So we have the material strength. The material strength is an inherent property of the material strength. And that right there is 250 pounds. So this is already set. It's the material strength, steel, and so on. Let's say using a steel beam. Now, we know the factor of safety that we're going to use is 1.67. That's what goes down here. And then this 150 is going to be the value that it's the allowable strength. So this really, when we rearrange it, the factor of safety is going to be that 250 right here over the 150, the 250 pounds over the 150 pounds. And that 250 pounds is the strength of the material strength. And we divide that by the 150, which is the allowable strength. So this is what's allowed, that we are allowed to load this at the allowable strength. And that is the definition of factor of safety. The material strength divided by what's allowed. The allowable strength gives us the factor of safety. Keep in mind for ASD, the factor of safety will be omega. In this case, we're assuming it's 1.67. So that's just a simple example. Now going here, we know we have ASD load combinations, and we look at these safety factors directly to the material strength rather than increasing the load. So we do not increase the loads. No, LRFD had the load combinations 1.2, 1.6. For ASD, we do not increase the loads. We use the service loads, and this ensures here a conservative design approach here when we apply the safety factors, which will be our omega. Here's an example of the nominal loads. So this is a service load, the real dead load. We just keep it. Dead plus live, dead plus either roof, S, or rain. We pick the highest one. Now note this is a little tricky. We're still not increasing the load still, so we're being consistent here. 0.75, so like 75% probability. So this reduces the live load. So this does it because we know it's very unlikely that we have a dead load, we have a live load, and we have either the one that controls here, whether roof live load, snow, or rain load, to occur at the same time. So what we can do here is reduce the live load and reduce this, the controlling one, because it's very unlikely that all of these will occur at the same time. So we can do that per standard in this case. And note, we do that the same here with the wind, earthquake, do that here as well. We do this again, reduce. We're not increasing for this one because it's very unlikely that all of these will occur at the same time as the service loads. So we can do that, but in the end, just remember, we're using the real service loads for ASD. The typical design steps, it's the same process. So identify the loads, calculate the service strength. So what we would do, get the dead loads, live, wind, earthquake loads. Here's an example. So now we're looking again still at the bending moment capacity. But for this one, don't use the factors. If we're using ASD, use the real dead load and live load, the service loads. So that means use the real distributed dead load, use the real distributed live load. Then we can calculate the ultimate moment, in this case, the ultimate strength for bending as an example as shown. Then we can calculate the nominal strength. Again, we can use the same formulas. Just as assumption, we're using the steel design equations. For concrete, we do not use ASD. It's only LRFD, so this is important. For steel design, we can get the nominal strength using the FE handbook formulas. Then we apply the safety factor. Again, keep in mind that the safety factor is going to be our omega for ASD. So that's important, not phi. Phi, resistance factor, is used for LRFD. And here we reduce the nominal strength to an allowable level. So in this case, it's always Mn over omega when we calculate the design strength per ASD. And for bending, it's going to be 1.67. For shear, it's going to be 1.50. Compression is going to be 1.67. So that's going to be the factor of safety, omega, and this gives us the allowable design strength. And then lastly, check the design requirement, the same design requirement we had up top, but the only difference now is we take Mn over omega for ASD, and that must be always greater than or equal to the ultimate strength that we saw above and calculated.